Computer simulation is widely used in technology today and really across a wide range of applications as well, from how air flows over the wing of an airplane to how traffic moves through a city or how an electrical circuit functions. Some problems, however, are extremely complex to simulate and cannot be solved today both accurately and quickly, even on the most powerful supercomputers. A good example is simulation of quantum systems, such as molecules or materials. That's actually very relevant, such simulations. It can help us design more quickly new medication. It can help us design materials that don't have electrical resistance or come up with new chemical compounds to be used in industry or agriculture. In a computer simulation, you can quickly generate and check many different versions of a molecule and compute their properties, avoiding thereby the expensive process of having to synthesize many molecules one after another to test in real life what their properties are.
Let's have a look at the theory.
The basis for any simulation is a model. A model is for us a simple description that captures the essential features of the object we're trying to simulate, whether it's the airplane or the electrical circuit. In the case of quantum systems, the model is a Hamiltonian. A Hamiltonian that is for us a large matrix with lots of numbers, and it contains the information about the basic elements of the molecule or material, the system we're trying to simulate. Plugging this Hamiltonian into a computer will allow this computer to find all the relevant properties of the system without ever having to build it in the lab. The difficulty is that if you do this on a conventional computer, it will take that computer exponential time, a time that goes up as 2 to the power n, where n is the number of particles that your molecule or material is composed of.
How can quantum solve this?
Quantum computers, on the other hand, have themselves an exponential complexity built in that matches the exponential complexity of the quantum systems they were trying to simulate, to compute. And as a result, a quantum computer requires only polynomial time, not exponential time, to simulate Hamiltonians of molecules or materials. Specifically, the time goes up as n to the power 3 instead of 2 to the power n, an exponential improvement and really the difference between being able to solve the problem or not.
What are the caveats?
A few final comments about the power and possibilities of Hamiltonian simulation. First, only certain properties can be actually simulated efficiently. For instance, the lowest energy of a molecule we can compute efficiently. But to describe the state, the lowest energy state in full, is exponentially complex, even for a quantum computer. Second, the result of simulation, any simulation, classical or quantum, is always just as good as the information that you put in. So the more accurate the information that you have to enter your Hamiltonian, the more accurate the results about the properties of the material, molecule that you're trying to simulate. So keeping in mind these caveats, still we think that the first important application of quantum computing will be Hamiltonian simulation.